Hey everyone, so welcome to my channel, and today we'll be looking into one problem statement, how we can validate a binary search tree. So we have given one tree and we have to validate if it's a binary search tree or not, right? So if I quickly talk about what is binary search tree, right, that is pretty important to understand, and I think I have talked about it in my previous videos, but let me just quickly brief about it. So binary search tree is about that any root node, right, any root node is given. Let's say if I take this tree as an example, we have 2, 1 and 3. This is our root node. So anything on the left side should be less than, okay, from the 2, and anything on the right side should be greater than 2, right? So basically if I talk about the value where it lies from for left and for the right side, okay, so if I write it about it, so let's write quickly. So let's say left, okay, so at the root we have something called lower bound and upper bound, right? I have talked about in previous, I'm just giving a proper definition. What is lower bound upper bound means is anything on the left side, what will be the lowest value possible and what is the highest value possible, that a value can lies in between these two, right? So for the left side, it for the first, if I just talk about 1, right, it's the minimum, right, whatever is the minimum value that is there, right, and what is the root value, which is 2 for this side, right? For the right side, we have whatever value lies in between the root value and whatever is the max value. So if left side any value lies in between this, for this tree it's basically there, that it's a BST, that particular node. If it lies outside of this basically lower and upper bound, it means it is not a BST tree, right? So I'll just give a quick dry run for this, and then I'll start giving a solution how it works. Okay, so let's take this as a tree, right? We have 5 on the left side, we have 1, right? So if I take 5 as an example, this will be 5 and this will be 5. This is for these two nodes, right? So can I say that one is the minimum and it's less than 5, right? So it means left check is correct, true, it's a binary BST. Can I say for 4, is it lying in between 5 and max values? So max is nothing, it's an int max, whatever is the max, right? And if I say what is a min, it's an int min, right? So can 4 lies in between 5x? No. So it means on the first level only we have returned that it's not a BST, right? Now let's assume that here it's 40 is there, we are assuming. After this assumption, if I take this is my I'm just replacing 4 to 40. Under this assumption I can say that 40 is lying in between 5 and int max, so it's a true. Now we can check other elements, right? Now let's check other elements. If it's a 40, can you tell me what will be the lower bound and upper bound for 6 and what will be the lower bound and upper bound for 3? That is a trick here. Okay, so let's say 3. Okay, so for 3 the lower bound will be whatever 5 is, that will be my lower bound, or whatever 4 is, that will be my lower bound. So if I again talk about what is the definition of BST is, whatever their parent node, the child node on the left side should be smaller than the parent node value. Okay, so under this assumption for 3, if I talk about for the left child, what will be the lower bound and upper bound? Lower bound would be the int min again. Is that true? Is that true? No. Okay, this will not be done. It should be less than 4. Sorry, 40 it is there, right? So it should be less than 40 but greater than 5. Again I am talking about it. Okay, it should be less than 40 and greater than 5, so it qualifies the BST. So if I talk about the complete, then it should be greater than 5 and less than 40. So I can say 5 and 40, right? For the right child, what it will be? For right child, anything max, right? So again it should be greater than 40 and whatever is the max. So if you see what is happening from top to bottom is, for 4, whatever is the value, okay, whatever is the 4 value, that is root dot value, if I talk about 4, that root dot value becomes the upper bound for the left tree and becomes the lower bound for the right tree, if I am correct. So I can say the 40 is nothing, it's a root dot val, and 40 is nothing, it's a root dot val. Okay, and what is 5? What is 5? 5 is nothing, it's a lower bound for 4, right? Because if I talk about 40, this 40 has a limit that it should be greater than 5 and less than int max. So whatever is coming from the top, so whatever upper bound is coming from the top, that becomes the lower bound for this. So I can say this is my upper bound. So upper bound is like, so for this 40, the lower bound is 5 and the upper bound is, so lower bound will become is limit. So this is the formula that we need to keep in mind whenever we are talking about the validation of BST or not. Okay, so let me do a quick dry run how the recursive approach works for this particular solution. Let's look into it. So this is my tree that I've just shown it, right? So let me select a pen, I'll take red. Okay, so now 5. So 5 here, if I write the lower bound and upper bound, lower bound is int min and the upper bound is max. Okay, now if I go on the left side, what I will do, I again have explained here for the left side, the lower bound and the root value. So lower bound, what it is, if I say here, this is my lower bound and this is my upper bound for the parent node anytime. Am I correct? Right? So anything from on the right side, it should be greater than the root value. Okay, and anything on the left side, it should be less than 5 and it should be greater than 5. Okay, so if I talk about what this value should be, this should be in between 5 and max, right? And what is max? So is it, this is 4, this is not correct, so let me correct it. So it's not correct, so it will return false. Here I'm just consuming the correct code, so it will return the false. On this side, what will be the lower bound? Lower bound will be my minimum, whatever minimum value possible. Okay, and whatever the root value, that will be my upper bound, that any value cannot cross 5, right? So this is my lower bound and upper bound for this. Is in one lies in between this? Yes. So this will return true. Okay, this will return false. Now let's assume for a minute, I'll just clean all of that and I take one more example. Let me just clean it quickly. So okay, done. Now let me take one more good example. Okay, let's say 5 and then here we have 2, here I have 1, here I have 10. Okay, now on the right side I have 11. Okay, now this is my tree. Now is it BST? No, it's not, because 10 is greater than 5. Now how we will solve this problem? So again, for the 5 we have, I'll take -1 and +1 as a greater than and less than, upper bound and lower bound. Assume this is a int min and this is a int max. Okay, now if I take on the left side, what will be my lower bound? Lower bound will be -1, that is coming from the up, and what will be my upper bound? Upper bound will be the whatever is the value. Okay, is 2 lies in between this? Yes. So this is my true. If it is true, then go and check their left and right tree. Now left tree, now whatever my value, that will become the upper bound, and whatever here from top is coming, -1 is the lower bound, right? That will be passed here also. So -1 and 2. Is it lies in between this? So I will say yes, true. Now again it will go to the left side. Okay, now here there is nothing, so I will just return true, because not for nothing it's already BST. Okay, now here I have written true. Now all these are true, nothing false we haven't right now encountered. Okay, so here from the left side true came. Now on the right side, what happens? On the right side, what will be my lower bound? Again I'm gonna say what will be my lower bound and what will be my upper bound. Upper bound is gonna be my 5. So whatever upper bound from up is coming, that is my upper bound. And what will be my lower bound? Lower bound is 2. It shouldn't be less than 2, because if it's less than 2, then it's not following the BST properties. BST is right child should be greater than parent value. So parent value say right child, it should be greater than, right? So 2 is my minimum and 5 is this, right? Whichever is coming from up, this is my upper bound. Okay, now here is this 10 lies in between this? No, so it will return false, right? Now here true and false, I will take end of this condition, I will return false. Now here it return false. Now here what happens in this situation, I will be passing two values, our lower bound and upper bound. What will be the minimum value? This will be my 5. So whatever value root dot value, that will become my lower bound. Here also if you see 2 is the become my lower bound on the right side, 5 is become on the lower bound for my right child, and whatever my upper bound is there, that will become the upper bound here also. So whatever upper bound is here, that will become upper bound. So 11 is lying in between this, yes, so it will return true. Now true and false, here it return false, here return true and false, it's false. So this will return that it's not a BST. Okay, now let's talk about quickly the time complexity, then I'll write the code, or let's write the code and then I'll talk about the space complexity and time complexity. Okay, let's quickly write the code. So what we'll do, we'll create one helper function. So we'll create it. So I'll just quickly give a little insight how we do recursive questions. So first we write the base case, we always do that. Second we write the recursion, and third we return the solution, right? So whenever we are writing the recursion, we have to see all possible solutions. So here the possible solution is left and right child, so we'll take left and right. Now with the left and right, if you see in the question when I was explaining the intuition behind it, we have to keep state in between whenever we are calling in left and right. What is the state we have to maintain? Left and lower bound and upper bound, we have to keep passing it whenever we are going to left and right. So we have to pass LB and UB, that is that name lower bound and upper bound, we have just taken the abbreviation for that, right? So to write this, what we can do, either we can modify this, or better we can just write one helper function. Let's not disturb our main function, and there only we can have these two values. So we will have one root. So let this is one class, so we have to pass the self. So this will be my root, and we'll have two values, upper and bound and lower bound, right? Now here we'll write the code. Now let me just write the typing also. This will help the interviewer to know, okay, if you are taking care of this, if you are in Python. And this will be nothing, it's my same here. This will not be an optional, so you can just take the tree node and put it here. Okay, now let's write the code. First thing, what will be my base case? Let me copy this, so this part will be writing here. Okay, let's just a minute. Okay, now we'll write these two cases here. Okay, and let me just call this method, assuming that this method will return my answer. And here I pass the, what is my lower bound and upper bound? I have already talked about it. For 5, any value is possible. So the minimum value is -1, the maximum value is 1 plus 1. That is nothing int min and int max. So in Python we do that this way. We do int -1 and then we do int +1. This is my max and this value. Now let's write the base case first. So base case is, as I said here, when we hit the no value, none, there is no left and right child. In that situation, whenever we hit the none, so what does it mean? There is no left and right child left. So in that situation, we'll return by default true, because it's a BST, there is nothing here. So I'm assuming that it's true. What will be my most important base case? That I'll be writing now. Okay, now assuming that we are on this 5. Okay, on this 5, do we have to check something? What we have to check? That this 5 should lie in between 1 and 1. So lower bound and upper bound, it shouldn't be outside. If it is outside, then it is not a BST. So let's write it the case. So if root dot value, okay, is greater than, if 5 is, so it should be lying after -1 and after +1. So this is my lower bound. If I say this is my lower bound and this is my upper bound, so if I light, so 5 should always be in this way, right? Now what I will be doing is, I will be saying the 5, that is root dot value, it never should be less than lb. Okay, it is always greater than, so I can say it should never less than lb. Okay, and it should never equal also. BST is like it should be less than, it should be greater, not even equal. If it's equal also, then it's not a BST. Or what is the negative if that happens? Or 5 should never be greater than upper bound, right? It shouldn't be outside of that. So root dot value shouldn't be greater than upper bound. If this happens, return false, because it's outside of the boundary, then it's not a BST. Now let's call the left and right child. So is my left child is BST. So I will just call this and I will do root dot left. Now what will be my lower bound and upper bound for the left part? So if you see on the left part, whatever lower bound, I pass it as it is, and whatever upper bound becomes the value. Then what I mean is 2 should be in between the lower bound and the whatever the value of the parent is. Okay, so if I say here, what will happen? Root lb and root dot when. If I say what is my right, so I'll call the right recursion stack, I'll call my right tree. Now for the right tree, if you see, for the right tree, it should always, whatever my root value, that become my lower bound, and whatever upper bound, it's as it is, it's upper bound. So what I mean is, when we are going down to the right or left stack, okay, so what I am doing from the top is I'm keep maintaining my lower bound, so it always be within -1. If you see here, it's -1 also. But for the right tree, I'm keep maintaining whatever upper bound I have set out for the parent child, that will go to the till n number of descendant of that particular child. Okay, to keep maintaining, okay, this is my upper bound, it shouldn't cross ever. Okay, so here what I will be doing is I will be passing root my values, my lower bound and upper bound, I'll pass it as it is, and both of them I will do left, and I'll do the end condition. Any one of them is false, it means it's not a BST. So this is my code, let's run it. Let's see if it passes all the test cases. Yep, it passes. Let's submit quickly, and let's see it's passing or not. So yeah, okay, one case it failed. Let's see what it might be. Okay, here I have missed one end. So basically, if one condition, if we take, it's a equal condition, right? So if I again submit it after adding this equal to, then it will work. So let's see. Okay, yeah, so it passes all the test cases. So this is about this BST, how we can validate it. Right now, let's discuss the time complexity. Anytime you are talking about time complexity, space complexity, simple rule: see any array. If you're talking about array, any array indexes, string indexes. If you're talking about tree, graph, try any node, if that node, how many times it's getting visited. Okay, so if I see in this whole recursion way, we are going top and to bottom to top, right? We see every node in a worst case. Let's say if this whole tree is like single skewed tree like this. Okay, so ideally it should go to the height of the tree, but if it's a skewed tree, in worst case every node will be going once, right? So this time complexity will come to O of n, and if I take space complexity, it will be recursion stack, which is O of n only. So when it is going, it's keep maintaining one recursion stack. So if I quickly write here, what will be my TC, it will be big O of n, and wait, big O of n, and my space complexity also going to be big O of n. I hope you understood this problem statement. This comes in a various companies, so understand the intuition behind it, try to solve it, and it will really help you. Hope you understood it. If you have any question, do leave in a comment, and thank you so much.